interested in this subject, and I don't know how to answer the questions I'm going to ask now. So these things all, I started considering these questions because I just shifted a little bit of my perspective. Dr. Fabio is not here because he knows our perspective. Okay, so this session is called Geometric Sets. All of the considerations I'm going to present today are ancient, age-old, and probably forgotten by many mathematicians now, because mathematicians usually work with coordinate systems and functions and so on. These things are ancient. These were concepts were introduced by people who never knew any coordinate system. For example, Thales. Thales 300 BC defined, for example, ellipse, hyperbola, and parabola, which we are going to review today. First, we would like to see what is meant by these are ancient. And usually not coordinate. Of course, if you have a coordinate, that would be better. Let me just leave before it sleeps. So the first concept is defined by defining Euclid's element called bisector. We have touched upon this already. Bisector, now I have borrowed from Dr. Fahimuddin's. I wanted to borrow his shoelace, but this is fine. Bisector in Euclid. Let us draw it, even if we have tried it before. So you have 2 points in the plane. Because I have now a compass which only can produce one distance, which we're going to use it, the compass which can do only one distance. So we have to have these points close by, otherwise if they are too far, then if this doesn't reach the half, then we cannot really do the bisector. Right? This was how Euclid did the bisector. Let me imitate. He puts one leg of the compass on one point, A, and then draw. If it is, oh, this one actually broke. If it is at least more than half of this length, you can actually do that even if it has only one distance. And then you do this, and then you do that, and then move the leg to the other point, which we call B, and then do the same. Now we are actually imitating nicely. So here we have intersection of those two pairs of circular arcs gives you exactly 2 points. By Euclid's second axiom, there is a unique straight line going through these. So we don't have a ruler, so we can't really, with shaky hands, we have to draw this nicely. You see? Not good. Let us try again. Don't put down upon this, because this is going to give us lots and lots, and it is not intersecting properly. So this straight line has a property that at every point of the straight line, distance to A is equal to distance to B. You have to notice that in here we have no coordinate system. We only have distance, and distance is enough for this. But in order to define it, now we can define it in matrix space. So let X be matrix space with distance function rho. Let X be a matrix space with distance function rho. And then let A, B be 2 points. Then we define bisector AB easily because we only use distance. And matrix space definitely has distance in it. It doesn't matter if distance is this straight or that straight. So this is a bisector, dimensional bisector, or the better name is equidistant point. A set, equidistant set, distance. And we use it because of this E. We can't use it P because we will now immediately generalize AB. Equidistant points, set of equidistant points for AB is equal to all points in the matrix space X, so that rho AX is equal to rho BX. Even this very simple definition, you can do lots of things about it. This is the bisector. Here, did we say A and B are equal or not equal? You could definitely assume that A and B are two distinct points in the plane. If it was just one point, what would he get by this method?
Point.
Whole plane, because
yes, sir.
when the distance is zero, the half, more than half of zero is positive.
All.
And then he can draw this intersection everywhere in the plane. So supposing that his compass can measure any distance and reproduce, any finite distance and reproduce, then the whole plane is in the bisector. And same thing, if A is equal to B, we will have to say that here, then EAB is equal to X. Right?
Yes.
In any matrix space. Even if this matrix space has 5 points in it, doesn't matter. Now, can you give me an example that this is empty? EAB exists a matrix space X and some points in it, some points AB in it, so that EAB is an empty set. I think Muhammad can manage that.
A and B lies on a plane.
On this line.
Yes.
But the line is not constructed yet. So you should really have it by now, because this is why we have been doing lots of things which are not matrix spaces so far, which are not the traditional matrix spaces. Graph. If you have a graph of matrix space whose distances are all integer, non-negative integers. So if your distance, if you have a distance which is not integer, then it will be empty. We will give more examples like this. If this example is not good enough, let me just remark that EAB can be empty. Even if ABR points in, can be empty. Already very interesting, because it can be whole space, it can be empty. This is the definition of bisector, the first and important geometric set in a matrix space I want to study. And then with this study, we have a paper on it, and we don't have anything more than that. So this is going to be, the paper is a very good paper. I shouldn't say paper is good. The journal is a good journal. So I see that the paper is in there. So I don't say that paper is good, but journal is definitely good. So even for bisectors, we have lots of problems. We're going to propose this later on. Now let us go back to 300 BC. Thales. I think it is Thales, right? Who defined the ellipses in the Euclidean plane, hyperbola in the Euclidean, hyperbolae in the Euclidean plane, and parabolae in the Euclidean plane. You still remember his definition? When I ask this question to our students all over the world, a parabola is y squared equal to 2px. But it was not Thales, but Thales had no coordinates. No coordinates. So he said something else.
Forward thing. I should define forward thing. Parabola or it's
Any one of them. Thales.
okay. For parabola, take a point and a straight line.
Yes.
Now every point which is equidistant from that
Point
point
and to the
will follow a parabola.
line is called. It was Thales.
Yes.
Let me just write it in brief here. Ellipse. Muhammad can give me the ellipse as well.
Yes. Take 2 points and then
the sum.
fix their sum.
Yes, all those points.
Those distances.
Points.
Yeah.
In the Euclidean planes always, I'm not going to write, the sum of whose distances to two fixed points is constant. We have now all forgotten about these pure geometric ancient Greek definitions. We have been very good because we have functional analysis, we have functions and curves and algebraic variety, all given in coordinates. And if I ask a question which has nothing to do with coordinates, young people don't know how to answer today. And then she fails the interview. Of course, the interview, I'm not always interviewing. The other guy can ask the same question. Distance is a constant. And hyperbola, and so the 2 points will be A, B. These are points.
I think in hyperbola the difference will be a constant.
Difference will be a constant. These were all from R squared, and C is positive real number. A non-negative real number in this case. In this case, non-negative real number. It's fine, it's just if you assume hyperbola. Hyperbola will be the sum is replaced by difference. Difference. I thought I might be doing some joint research with some of my colleagues, but I think I will just simply need to recruit Muhammad first and then some gentleman here. If you are interested. If you are not interested, I will not force you to collaborate with me, always. Now I will erase this. Here the only thing which is used is distance, also in here. And parabola, Muhammad already said it, I'm not going to write it out completely. And then we will see, we will now, in this space, I will define this for metric spaces. Because we now have the metric space and the distance. You will see that this is zero level easy. But can you answer the questions which I'm going to ask about them? It has no prerequisite. Zero level easy, positive. So now X here metric space with distance function rho, and A, B are 2 points. We are not going to define parabola yet. And C is let us assume that it's a positive real number. Then we can rewrite the names. An ellipse in X is E. Let us use another. E is fine. Let's set E, which is all those points X in X, such that rho AX plus rho BX is C. Isn't it beautiful? And ground, isn't it ground level? It's ground level, we only need the definition of a metric space, nothing else, and then we can define such a set. Hyperbola, just change this into minus sign. Many people, when they started looking at these things, they look down upon it. Oh no, this should be all known. You decide, I don't want to decide for you, decide which are known, which are not. We want to study something like high spaces and things like that, but in high spaces there are also metric spaces and these objects are not known. In my opinion, minus is equal to C. And we hold on to the parabola before we find an appropriate, suitable concept which is analogous to a straight line in Euclidean plane. Of course, you can take any subset, but we're not doing it. Now, we will display graphics. And we'll go slowly through this. What are we now? Every time it asks to detect a Wi-Fi. So we'll go through this slowly, so that we can all digest the food, which may be tasty, which may be not tasty. Some people think that one man's food is another man's poison. Shakespeare said, he copied it from somewhere else. Shakespeare said this. This food is, to me, it's a food for the king. But maybe some people don't like it. What happened? It has gone outside the screen. And you might here. Yes, on the edge, and then I need to try to change the edge. So that if I magnify full screen, it's going to go outside the screen. Hey, no, it is. Okay, we move it here. And then we have geometric shapes. So we define these already. This is a bisector, simple bisector over there. And here we have ellipse and parabola. You see, it's outside the screen. Maybe I should use a normal size of slide. Once you have every one of you is using somewhere Spain or Madrid or somewhere that template you always copy without understanding. These are the two definitions which I wrote there. Now, question. This question is the first question I can't answer. Given any metric space with distance function rho, characterize ellipse and hyperbola. We will still hold on to the parabola at the moment. It is going to be horribly difficult because you know where it is all very nicely characterized, which metric space in which. These are all completely not done if you have taken a good course in analytic geometry. These are all done in Euclidean spaces already, right? In the Euclidean plane, there are analytic geometry which should go on proving 5 different definitions are equivalent to each other. This definition, conic section definition, which you need to intersect the right circular cone with a plane, and then you get the intersection to be satisfying these conditions, or giving quadratic equations. And then if you have any quadratic equations of 2 variables, then you can reduce it by rotation and translation into one of those standard, the canonical conic sections, namely ellipse, hyperbola, parabola, or degenerate one. After that is done, you start with standard canonical conic sections and prove that they satisfy this definition. Then you will be able to prove that all 5 definitions are equivalent. Geometric, conic section definition, algebraic, the quadratic equation, and the standard, so on. But there's another definition there somewhere, I don't know. And not only so, in linear algebra, if you have done linear algebra nicely, I think here you are doing it nicely using advanced linear algebra. Every quadratic form in any Euclidean space is characterized. You can actually reduce it down to its normal form. And then you have this far the signs are all plus, and after that it's minus and so on. This kind of idea. Then you essentially you know everything about quadratic forms in any Euclidean space of any dimension. That is known. That is the only thing we know so far. How about if you even have if you even look at the geometric space? Remember that we have told you already that geometric spaces are three. One is Euclidean spaces with a curvature everywhere constant 0. The other one is Riemann spaces, curvature everywhere constant 1 of any dimension, of course, because Riemann sphere we have seen all the time. But there is three-dimensional Riemann sphere as well. Hyperbolic geometry in which everywhere the curvature is negative 1. Now, in Euclidean spaces, these three types of geometric sets are classified or determined completely. And we understand it by even looking at equations, which is good because I'm not saying equations are bad. Only that you need to not really forget the original definition. And what about for Riemann spaces? What are using its own intrinsic metric, of course, this time the metric is the metric along arcs. According to that arc, in any Riemann space, what is ellipsis like? I'm trying to guess that it is always a circle, but I'm not able to prove it actually. How about in hyperbolic spaces? What are the ellipses and the hyperbolas like? And you need to also make sure that in R3, this same definition, this is now R3, this same definition, what does it give you? Ellipsoid.
Ellipsoid.
And that will give you hyperboloid. But hyperboloid even have two different types. So even in R3, this is not quite like in R2, in Euclidean plane. And then geometric spaces we don't know. Geometric spaces other than I. Geometric spaces other than I in that question, I don't know the answer. I don't think it is horribly difficult, but it needs some hard work and some sort of ideas to do it. How about if you go slightly more general than the geometric spaces, what do you get after that? The spaces which contain geometric spaces as extreme special example. Geometric spaces contain Euclidean spaces as extreme, one third of the examples. What is just above geometric spaces? What does geometric spaces have in common? Geometric spaces, we have just said that the curvature is at every point the curvature is constant.
Yes.
Which means when you're moving in the space anywhere, you don't know where you are. So that means that the group of isometry is transitive on the space. So if a space has if you have a metric space, even a differentiable manifold, for which its group of isometry, let us say, but there are other groups as well, acts transitively on it. So every 2 points can be mapped by some group element from one to the other. Those spaces we don't know. That is the one next level. If you go now slightly more than that, you come into what is called Riemann surfaces. In dimension 2 only, Riemann surfaces, we don't know. And I will now have to display the proper definition of a Riemann surface. In any Riemann surface, what are metric, like yesterday's talk was very interesting to me. But he changed the definition and get the variation of the metric. We're exclusively talking about the classical metrics. We don't even change that, and we don't know these beautiful sets how they are like. Riemann surfaces. This is the definition here. And I'll go back. This is the definition of a Riemann surface. WZ are complex numbers. F is a polynomial with complex coefficients of two variables. And you only need one single equation, polynomial equation equal to 0. And its solution set will give you a one-dimensional complex manifold or a two-dimensional real manifold. That is called the Riemann surface. This is a modern definition. The original definition was when you were doing your complex valued function of one complex variable. The lecturers in Pakistan or in China would have told you that it is the domain of entire functions, holomorphic functions, or analytic functions. Or some teachers will say it is an image of holomorphic functions. But those two definitions are contained in this here. If you look at W as the function value, then you have the image. If you look at, if you solve Z out from that equation, you get the domain. This is a symmetric modern definition, so easier to work on, because this now gives us algebraic variety with one, which is given by one polynomial equation. Complex, affine, algebraic variety with one polynomial